I am most pleased that Philip Castro is here. He talks in this usually sort of controversial position right before spring break, but he did it with joy. And he's going to tell us about multi-objective optimization. And all I can say is be gentle.
All right, thank you, Jim. So I'm Philip. I'm a fourth-year graduate student over here in the math department, and I'm working on my PhD dissertation now, and I'm looking at multi-objective optimization, more specifically looking at how it can be applied to decision making and things like that. So just wanted to kind of show you what I do and give you a little bit another way to think about some of these optimization problems. So a quick overview is a map of where we're going. We're going to talk about motivation, so we'll kind of have a cute little motivational example. We'll talk about some background, so we'll talk about definitions, different concepts, go over our notation. Then we'll look at two specific solution methods. So these are kind of classic ways of solving these multi-objective problems. One of them is called the weighted sum method, and the other one is the epsilon constraint method. And then while looking at those methods, we'll work through an example so you can kind of see it on an actual mathematical case, and then we'll conclude. So here's the motivation. Suppose I'm in the market for a new car. And so I look at my car options, and I'm going to score them on various criteria, right? I'm going to score them on their safety rating. I'm going to score them on their speed, and then I'm going to score them on their looks, right? So the Ford Focus, super safe. I give it a score of 10. Speed, it's not so great, so I give it a 3, and looks a 3. The Kia Soul, the safety is a 5, but speed and looks is not so good as a 2. So sorry if you have a Kia Soul. I'm not trying to throw shade here, but just an example. The Subaru WRX, that's got a safety of 5 and speed is 7, looks are 7, and then of course the Ferrari, right? It's going to score great with that speed, looks, but I can't trust myself in that, so I got to lower its score, safety score a bit. So looking at this, right, we want to compare each of our different options, right? And that each option is our car, and our criteria again is the safety, the speed, and the looks. And so how do we pick the best one, right? So how should I look at this this ranking and decide which car is the best one for me? Well, one hint at answering that question is I shouldn't pick the Kia Soul, right? And here's why. Because what we see here is that if we compare, for example, the Kia Soul with the Ford Focus, it's dominated by the Ford Focus in every way, right? The Ford Focus scores much higher in safety, it scores higher in speed, and scores higher in the looks, right? So we say that the Kia Soul then is dominated, right? We would say that that's a dominated solution. And so, of course, if we're trying to pick the best, right, we don't want to pick something that dominates. We want to pick something that actually has something better than it, right? So let's look at our other 3 options. So, right, remember we're looking at the Ford, the Subaru, and the Ferrari. Well, if we compare those, right, what we see is that, for example, if we compare the Ford Focus with the Subaru, the Ford Focus does much better than the Subaru in safety, but the Subaru does much better in speeds and looks, right? So we can't really compare those two. Same thing if we compare the Ford Focus with the Ferrari and then the Subaru with the Ferrari, right? So what we're seeing here is that now my decision is down to these 3 options, and now I have to basically look at the trade-offs, right? I have to see, am I willing to trade off this much safety for this much in speed? Am I willing to trade off this much in speed for this much in looks, et cetera, right? So basically what we have found here are so-called non-dominated solutions, right? And that's kind of gets at the heart of multi-objective optimization. That's really what we're all about. So this is kind of a silly example, right? So there are real examples of multi-objective optimization. So one of the big ones is portfolio optimization, right? So if you're investing in the stock market, or you're trying to figure out your IRA portfolio, whatever it is, right? Something that you'd be interested in optimizing is your risk and return, right? You want to minimize the amount of risk you incur while maximizing the amount of return in, right? Kind of intro economics tells us that, right, those things are typically in conflict with each other, right? If the higher the risk, the higher the return, usually the higher the risk, right? So we have to deal with some trade-offs there. Another classic example is engineering design, right? So for example, if you're building a car, you want to be able to figure out the best place to put, your battery, for example, while trying to optimize different things. Like you want to have a battery that is not too big, it's not too small. You want to make sure that it's easy to repair the car if you put the battery in a particular location, et cetera, et cetera. Emergency planning, right? So if we're looking at, for example, an organization like FEMA would be doing this type of things. So you'd want to minimize the cost of stockpiling your supplies, right? Because it costs money to keep those things fresh and ready to go. But you also want to be careful that you don't, minimize costs so much that you have so few supplies that when there's a huge need, you're not able to meet it, right? So we have to balance those as well. And then finally, another example would be natural resource management, right? So for example, if you have a hydroelectric dam, you want to maximize the electricity you're producing, but at the same time, you want to ensure that the ecosystem of the water is good for the fish and the frogs and I don't know, whatever those lakes. Loch Ness, the Loch Ness monster, yeah, Nessie. We want Nessie to have a nice pool. So those are some real examples, and so the examples I've given are all bi-objective in the sense that we're only thinking about 2 objectives at a time, but oftentimes these problems will have many more. It's not uncommon to see problems that have 4 to 8 objectives at a time. So now that we kind of have a foundation for what we want to do and what types of things we're trying to solve with multi-objective optimization, we can look at some definitions. So first of all, we need to talk about ordering, right? How do we compare vectors? And so we're going to define that right here. So we pick 2 vectors, u and v, in reals RP. We say that u is less than v if and only if each component of u is less than each component of v, right? And this is the strict inequality. Then we have u is less than or equal to v, which the way that I read this, I don't think this is standard practice, but it helps me keep things straight in my head with some of these different orderings. U is less than or almost equal to v, if and only if each component of u is less than or equal to v, with the exception that you have to have at least one component that is strictly less than v. Okay, right? So you can't have exact equality here. You have to differ in at least one component. Right? So that's why, right, I call it less than or almost equal to. But then, right, the next step would be less than or equal to, right? So that's where we have the double equal sign underneath, and that's where, right, they can be equal to each other.
So if u equals v and u is not less than or equal to v, then that's the second one.
That is correct. If u equals v, then we can't say that u is less than or almost equal to v, right? We would be able to say case 3 holds, right? So yeah. So this notation and these definitions give us some more flexibility in thinking about what trade-offs are we interested in, right? How do we measure trade-offs and how do we find optimality in these multi-objective problems? So with that in mind, we can finally look and formulate our generic multi-objective problem, right? So it looks similar to what we would do for single objective, right? Except that we have a vector valued objective function now, right? So vector value means you give it vectors and it'll spit out vectors, right? And so that's f of x, and each component of f is given by f1, f2, ... fp, subject to some constraint set, right? Call it x. So x is gonna, capital X, that's gonna be a subset of Rn, and each of the components of our objective function are real value, right? So for the time being, and actually for the purpose of this talk, we're not gonna really assume any structure on our function f, right? We're not gonna really worry about continuity or convexity or differentiability, etc. But this is the generic form for a multi-objective problem. So typically, in the context of multi-objective optimization, because usually we use these types of problems to model decisions, right? Actual decision making. We'll typically call the feasible region, right? The set of our constraints, the decision space. And again, in general, we're not going to, we typically don't have a unique optimal solution, right? You're typically going to end up with multiple, right? Because again, we're thinking about objectives that conflict with each other. So, right, again, if you think about return versus risk, right, there's going to be different ways for you to be able to trade off rates of risk and rates of return. You're not going to both be able to optimize those to their optimum. And so that set that contains all of those optimal solutions, we call that the Pareto efficient set. And that's related to our definition of optimality, right? This idea of efficiency, which we'll get to. So in essence, those points that are our Pareto efficient points are those non-dominated points. So remember from our car example, right? We would say that the Ford Focus, the Subaru, and the Ferrari are non-dominated. And so those would constitute our Pareto efficient set. Or just efficient set, right? It's a mouthful to say Pareto and efficient, so efficient. All right, so definitions then. This is what we mean by optimality. So when you see this problem and it says to minimize, this is what we mean by minimize, okay? We have three different notions of efficiency here. So first is weak efficiency, right? And so basically, if we have a decision in our decision space, we say that it's weakly efficient if I can't find another decision in my decision space such that my objective f of x is less than f of x hat, right? And that's the strict less than, right? So basically, the reason that we define it in terms of with a negative, right? We don't give a positive definition. We say there is no rather than there is because talking about it being there is no other decision helps get at this idea of trade-offs, right? Helps get at this idea that's the best you can possibly do. If you do any better, you're going to have to deal with trade-offs. So I'm sure you could guess what the next notion of efficiency is. And that's going to be, we say that x hat is efficient if you can't find a decision such that f of x is less than or almost equal to f of x hat, right? And then the next one we call strictly efficient, which is there's no other decision such that f of x is less than or equal to f of x hat. So we'll see some examples of this to get a better idea of how these definitions play out. But intuitively, what you should walk away from it intuitively, this is how we talk about trade-offs. This is how we talk about the best you can possibly do. So just words of the trade. If x hat is efficient, we say that f of x hat is Pareto or non-dominated, right? So we can talk about things in the decision space, but then we also have language for talking about them in the what's called the criterion space, right? That would be the image of your decision space. We good? Any questions so far? Okay. So let's see this definition of efficiency in action, and let's go back to our example of looking at the car.
I do have a question on the previous slide. For the strictly inefficient. You mean x, no x other than x hat?
Yes, you're right. Yeah, that's good point. That's a typo. I should include that. Yeah. Yeah, so no point other than x hat, right, than what that you have, since we can allow equality with that third point. Thank you. So efficiency being in this example, right? So comparing all of these points, right? We can see that the Ford, the Subaru, and the Ferrari are all efficient, right? Because I can't find another car in this list in my decision space that does better than the Ford, the Subaru, the Ferrari. However, the Kia, right, is not efficient because I can do better, right? In particular, we saw that it can do better with the Ford Focus. So, right, comparing the vectors across the rows, you can see that. So, notation, we want to specify what our efficient set is. And so we typically do it like this. And so the set of strictly efficient solutions we denote with a x sub SE. That is contained in the set of efficient solutions, which is just x sub E, which is contained in the set of weakly efficient solutions, x sub WE, right? And obviously that's contained in the decision space. And then we have some notation for our outcome space or criterion space, right? We denote that with a Y. And so then we talk about the set of non-dominated solutions, or right, strictly dominated or weakly dominated, right? You'd add the corresponding S or W to that subscript, but it's just Y sub P. That's our set of non-dominated solutions. And of course, right, Y sub P is the image of X sub P, right? So if you have your efficient set and you plug it into your objective function, of course you're going to get Y sub P as your image. So yes.
What if F is non-deterministic?
That is I don't know. That's a part of research that I'm not totally aware of. I usually work in deterministic type stuff. So, but that is a whole other area of this type of stuff. All right. So real quick, we have a very nice property of the non-dominated set, which, right, that should be Y sub P, not Y sub N. And this property is that whenever you have a non-dominated set, it'll always be contained in the boundary of your set. Okay, that's all that this is saying. And so we have this great picture that I drew. I know all of you are thinking I shouldn't be in math. I should be in art school. You flatter me. You know, but I want to give those artists a chance to actually make a name for themselves, you know. But what we see here, right, is Y, that's our criterion set, right? The blue that I have marked there, that's our boundary, right, because it's the edge of our set. And then the red, that's our non-dominated, right? So that's on our boundary. And so in general, whenever we're looking at a minimization problem for a multi-objective problem, we always know that the non-dominated set is going to be on the southwest quadrant of your outcome set.
Right. What are you assuming on your function now, though? Are you assuming any kind of continuity?
In this little example, no, we're not really assuming anything. This is just kind of a, because you can't have a broken Pareto set, right? It doesn't have to be connected. It doesn't have to be continuous. And typically what we talk about is convexity. And so your problem, right? Your decision space may be convex, but in general, you don't expect your outcome set to be convex.
I mean, even if the function is not continuous, it still forces the YP into the boundary. Huh?
Mm-hmm.
It's interesting.
Yeah. And there's some nice geometric interpretations and understanding of this. Like one of the main ways that you can define this idea of efficiency is using cones and things like that. And that's a very nice geometric way of looking at it. But I would direct you to the book that I used if that's something you wanted to. But it's actually pretty intuitive. Like this definition for efficiency is pretty intuitive. Right, because we can get into that real quick. I wonder if I can get my mouse to show. There. So, right, if I'm somewhere here in my outcome set, right, and I want to minimize F1 and F2, right, that's going to be to the left for F1 and down for F2. And so if I'm minimizing, I'm going to be moving until I hit the boundary, right? And then when you're on the boundary, right, I can't go past because I won't be feasible. And so all I can do is move up and down, basically. So then you can move up and down there. But if I move too far to the right, for example, over here, then I'm no longer efficient, right? Because I'm dominated by things further to the left. Right? So, and then if I move too far up here, right, then I'm dominated by things below me. So that's kind of the intuition behind this. And that follows from thinking about cones and all of that, which are special sets with special structure. Does that make sense? Okay. So with all of that in play, now we can start thinking about, okay, well, now how do we actually solve this? Right? I mean, how in the world do we start expressing each of these functions, right? I mean, one thing that you could try doing is just minimizing each one individually, right? But remember, we still have to deal with trade-offs, right? I may make one smaller, but the solution that minimizes this one might make another function bigger, right? So we don't want to just separate them out. We want to kind of keep them together and have them communicate with each other so that we can measure those trade-offs. So any ideas about what we can do?
I mean, the easiest way is you can just have someone tell you which of these factors is most important to you in like a rank ordering.
Yeah.
But if someone is willing to do that, then like hold on to that person because you're not going to find another one.
Yeah, exactly. Exactly. So that's a good point, right? And actually a lot of methods that end up coming out of this use that idea, right? The idea is that, you know, you have the decision maker and then you have the analyst. The analyst goes to the decision maker and says, so come on, like, what do you actually care about, right? And then the decision maker would tell the analyst, hopefully would tell the analyst, and the analyst would then be able to go and use that type of weighting information, right? Weighting these functions. And I just give a big hint, weighting, W-E-I-G-H-T.
So yeah, in fact, in engineering, we use that all the time, in design problems. So
Yeah, exactly.
you have 6 design criteria that you want to maximize.
Exactly.
Then you give weightage to each one of them, and then you have just basically one function.
Exactly. Exactly. So, right, one idea that we have is to try and rather than trying to do all of these functions at the same time, turn them all into one function, right? Because we're really good at solving single objective, right? I mean, there's no shortage of theory and methods for doing that. So there might be some ideas here, right? So how can we do this? We do it by scalarizing. All right, so to see that, and that's basically what the weighted sum method and epsilon constraint do, right? They're two different ways for taking this multi-objective problem and turning it into a single objective problem. And there's kind of two different perspectives on doing that. So here's a mathematical example. It has no, it looked nice when I graphed it. That's why I picked it. So that's the only reason we have it. So it's a bijective problem. The first function is linear. The second one is quadratic. And then we have a subject to some constraints. In particular, it's basically just right the upper part of a parabola. And I have some graphs to show you so we can get an idea of what this looks like. So we're going to let X, our decision space, just be that feasible region, right? Whatever everything is subject to. And there's our feasible region, right? So we kind of have a parabola, and it's bounded above by 4, bounded to the left by 0, and then we're going to take everything that's above that parabola, right? And then if we look at the image space, right? So the criterion space, this is what it looks like. We have a nice little curve, and right, remembering our result that the Pareto set's always in the boundary, right? We can already see where the Pareto set should be, right? And that should be right here, the southwest edge, all the way down, probably to about here. Right? So I just want to caution you that don't think that in general, right, you'll be able to just throw a plot up and say, oh, there's my efficient set. Right, because this is simple and nice because we have it's bijective, but as soon as you start having more dimensions, I mean, good luck trying to see what the Pareto set is in 4 dimensions. I mean, if you can see in 4 dimensions, maybe you should start selling tickets or something. I don't know. But right, so we don't want to just depend upon a graphical solution method. But again, for example, this is a good way. We have an idea of where that set's going to be. So this is the problem that we're trying to solve. We're trying to actually find those Pareto points. And so to try to scalarize this, right? And so the first idea, right, is this idea of weighting. So let's talk about what function is more important to us compared to others. And that basically gives us the weighted sum method, right? So looking back at our generic multi-objective problem, right, we have our P objectives. Well, let's just assign weights to each one, right? And these weights are they can represent importance to a decision maker. They can represent, well, right, that's typically the main interpretation of them if you're not just doing this as a mathematical solution. So, right, it's importance of these weights. And by convention, we're going to choose the weights to be between 0 and 1, such that the sum of the weights equals 1, right? Again, since we can think of this like percentages, right? We want the whole percentage of all of the weights to add to 100%. And so basically what we want to do is if we try a bunch of different combinations of weights, right? We kind of pick some combinations and permute them and solve this problem over and over and over and over again, right? We should be able to find some set of efficient solutions, right? At least that's what we hope for. We need to make sure that if we solve this problem, we're getting efficient points, right? So we have some results about that. And in particular, we have this proposition. And so if you have an optimal solution to your weighted sum method problem for some vector of weights, then the following holds. If the weights are greater than or almost equal to 0, right? So basically you can't include the 0 vector. It has to be at least greater than 0. You can always guarantee it's weakly efficient, right? And interestingly, most of these methods that you end up seeing without some sort of special conditions, typically you're only going to really find weakly efficient. That's typically the best thing you'll be able to do. However, if I pick weights that are strictly greater than 0, right? So all of them are non-zero, then I can guarantee efficiency. And if you have a unique optimal solution with a set of weights, then you can say that it's strictly efficient, right? So you won't always end up with a unique optimal solution. So typically you're going to be in case 1 or 2, but there are problems where you can't end up in case 3. So let's think about the proof, right? We're going to use the classic method. It's so great. It's probably one of the best ways to prove things. You do it. Eric Gott's book, which I have the site for at the end of the presentation, presents the proof of it. If you actually want to see how to do it, but we're not going to do it here. So let's see this on our example. So let's pick some weights. Let's just pick some, non-zero weights, right? So we're going to have W1 equals 0.025 and W2, right? Again, they have to sum to 1. So, right, we're forced to choose W2 to be 0.75. So then we scalarize it and we had to solve this problem, right? So we put a weight of 0.25 on our first objective function and 0.75 on our second objective function. And then we have our constraints and we do the minimization. In particular, we do some MATLAB magic. And we have an optimal solution. So that's our optimal solution. Right now, that's not particularly meaningful. So let's look at the graph. So here on the graph is our image set. I solved this for a couple of different, more than a couple, quite a lot, different weights. Let me get this there. So I did it for 7 weights for the weighted sum method, and so we were looking at optimal value 0.0. So we're looking at somewhere over here is the point that we found, right? But I did it for many different weights. And so what's interesting is, right, we don't really get a very good representation of our efficient set, right? We get a bunch of points down here, and it's kind of much more sparse as we go out in the Pareto set. So obviously what we see here is that there's limits to this weighted sum, right? You're not going to be able to just take any old problem and throw weighted sum at it and expect that you're going to get something that's actually going to give you good solutions, right? Because you can, what you end up here, if you solve this problem, you end up with a lot of different solutions, but many of them go to the same Pareto point, right? Because again, you can't guarantee optimality of that weighted sum method. Not always guaranteed, right? So there's still room here, right? There's still room for improvement. There's still room for doing more research and studying what problems does weighted sum work well for, what problems does it not work well for, etc. Right? But at the very least, we're able to find a good number of them. And again, just like we saw from our intuition, we see that they are indeed Pareto, right? Because they're right there on the boundary. All right. So that's idea number one, right? The idea number one was basically I'm spoiling the surprise. There. Idea number one was let's keep the objective functions. We'll put weights on the objective functions, right? But we're not going to mess with the constraints. We'll keep the constraints the same. The other idea is to try and what would happen if we would put the objective functions in the constraints, right? And we would put a bound on that objective function. And that's basically the idea of the epsilon constraint method, right? So you're going to pick a particular objective function that you're interested in minimizing. And that might be the one that you're most interested in. It might be the one that is particularly representative of the part of the Pareto set you're interested in, whatever your criteria might be. And then you'll pick upper bounds for the rest of your objective functions, and you'll throw them in the constraint set, right? So this way, basically, you're looking at your entire constraint set, or you're looking at your entire decision space, but you're limiting it, right? Because now you're only interested in decisions that makes sure that your other objective functions don't get too big. Right? You want to keep those as small as possible, right? And you can do this for any number of objective functions, right? It kind of gets unwieldy pretty quickly. And it can be problematic when you start throwing constraints in, particularly if they're, non-convex or, quadratic, etc. Like things can get weird. But in principle, it does work. And so this method is actually a generalization of the portfolio optimization model that was discovered by Markowitz in the 50s or 60s, I think, Harry Markowitz. It's a classic paper of multi-objective optimization, but also, right, mathematical finance, where basically, right, he wanted to maximize return and minimize risk. And so basically what he would do is he would, have a maximization problem. And so maximize return, but then he would throw the risk, measure the function for risk in your constraint set and say, but I don't want to incur more risk than epsilon, right? So it's actually very natural, right? It should be, right, at least a very natural kind of intuitive way of thinking about this. Yeah, I want to put a bound on my risk, but I want to, with that bound on my risk, I want to do as well as I can with my return. And so taking that idea and generalizing it, you end up with the epsilon constraint method, right? So again, pick upper bounds on your objective functions and only minimize one of them. So let's see this at play. Well, not yet. Actually, we're going to look at some results. So if you have an optimal solution of your epsilon constraint method, then you can guarantee it's weakly efficient. Great. That's what we want, right? Whenever we do these methods, we always want to make sure you're solving the original problem and not just solving some random single objective problem. So we can guarantee that we're going to get weakly efficient. However, if we have a unique optimal solution to the epsilon constraint method, then we can do better. We can guarantee that it's efficient. So that's nice. And then finally, we have a nice if and only if, right? So this is a nice kind of holistic view of this problem, right? So if you have something that is efficient, it's efficient if and only if you can find some epsilon, right? Some upper bound on all of your objective functions, such that x hat is an optimal solution of your epsilon constraint problem for all k. Now remember what k is. K is the index on your objective function. Right? So the idea here is if you can find one epsilon such that if you rotate out which function you have in your objective, right, which one you're actually minimizing, and each time you get x hat as the optimal solution, then it's efficient. So that's what that result is saying. And that's a big result. So we should probably prove it, right? Go ahead and read it. It's not terribly hard. There's a couple of results that build up to it. But just so I guess for your information, right? When you are doing these types of problems, when you are trying to prove that your method is giving you efficient solutions, typically the technique used is proof by contradiction, right? And that's very useful, especially because we have efficiency defined in terms of a negative, right? So if there is no X, contradiction would say, well, suppose there is one, right? And then you show that if there is one, you divide by 0 and the world implodes, whatever, right? Whatever your contradiction is.
So would this work for only like 2 objective functions, or?
It's definitely ideal for that, but you can do it for different ones. Yeah, you can do it for many.
So how would you do it? Would you put constraints on 3 of them and minimize the 4th one?
Yeah, exactly. So whichever one you were most interested in minimizing, right? That's the one you'll put in your objective.
Right.
And you put upper bounds on the other ones.
Okay.
All right, so let's look at our example again. We want to minimize F1 and we're going to put F2 as a constraint, and we're going to let epsilon equal 2.5. Something random. Oh, I messed up the LaTeX here. So this x1 minus 2x2 should be right here next to the minimize, right? Because that's our objective function. So we're going to be minimizing x1 minus 2x2 subject to, right? We have our f2 is bounded above by 2.5, and then we have, right, the rest of our constraints, the parabola, the upper bound, and all of that stuff. So this is the problem we're minimizing, right? And it's actually kind of elegant, right? I mean, we went from this kind of ungainly bi-objective problem, and now it's very nice to look at. Now we can only think about minimizing a linear objective. And yeah, we have to deal with a quadratic constraint, but you know, we can deal with that. Like, it's okay. So again, doing some MATLAB magic, optimal solution and our optimal value. So we have an optimal value of -2.6 and 4. So again, let's look at that up here. So -2.6, right? So that's maybe around here is the point that we found. But again, right, we're still not doing super great, right? We still haven't really found the entire Pareto set. We just found a little chunk of it. Although this one's maybe a bit nicer than weighted sum, right? Because they're all in a nice line. But there's still work to be done, right? There's still more theory that's needed to be able to really be more comprehensive in solving this type of a bi-objective problem. But there we go. That's what our weighted sum finds us. And in case you're wondering how I did this, basically, I solved this problem and I iterated over the constraint 2.5, and right, and I started from epsilon equals 0 and I went up to 4, right? Because the upper bound for F2 is 4, and just took a step size of whatever 0.1 or 0.05 or something like that. And you just solve that problem over and over and over again. And so we end up with that. So we can actually see both of our methods together. So in black is our weighted sum, and blue is the epsilon constraint. And so we can see kind of how they solve our set. And so it looks like both of these methods, right, they really like the bottom edge of our Pareto set. They were very good at finding our solutions there, not so much higher up. So in conclusion, right, those are kind of the two classical methods, right? So those are the ones that when you have nice problems that you're dealing with, those are the ones that you should definitely throw at it, right? So again, if you're thinking about doing some investing, right, epsilon constraint method would be very natural to try for that. But in conclusion, multi-objective optimization, right? One of the great things that it does, really enriches our ability to model different problems, right? Rather than only thinking about, well, I can only minimize my costs, right? You can also minimize cost and waste at the same time, or you can maximize revenue while minimizing costs at the same time. Right? You don't have to think of these things exclusively. So it really helps us to model these decision problems. However, right, it does bring some more complications, right? Because you do have these extra objective functions. You have to think about how you're going to deal with them. And so, in addition to that, there are other notions of optimality, right? There are relaxations of efficiency. And some of them are called something like epsilon efficiency, where you kind of loosen what is necessary for efficiency. There's lexicographic optimality, right? So you want objective functions that are lexicographically dominant, right? So if you think about the dictionary, right? Everything's alphabetical order, right? You want the one that is first in line of the dictionary. That's kind of the idea of lexicographic optimality. And there's lots of others depending on your problem and what you're interested in. So one of our solution techniques is to turn a multi-objective problem to a single objective problem, right? Typically we call this a deterministic method. And what we really mean by that is that I can prove optimality to you, right? I can prove that if you do this problem, you're going to get weak efficiency. And if you have these conditions, you're going to get efficiency. And if you have these extra ones, you'll have strict efficiency, right? I have verifiable proof that it will solve the multi-objective problem. There are other methods though, right? And this is one that you'll typically see in engineering problems, especially because they're just huge problems. And these deterministic methods or classical methods, right, can't always handle them. And so one of these heuristic methods that's a lot of work is being done on them now are called genetic algorithms. Right? So the reason that they're heuristic though is that typically you can't prove convergence, right? So the way that this algorithm works, that it computes a candidate Pareto set, and then if you're happy with it, keep it. If not, it'll compute a new candidate Pareto set, a new, right, and keep going. But so it's this process, you're creating a sequence, right? But you can't always guarantee convergence to optimality, right? Sometimes you just kind of have to say, oh, well, I guess I ran it long enough, and so it's probably pretty good. Which, again, for the application, typically in engineering, for the application, you're not always interested in optimality. You're just interested in good enough, so it does do the trick. And again, we saw that these types of problems can be in a whole myriad of applications, right? From investing, natural resource management, engineering design, you name it. There's probably a journal out there dedicated to multi-objective optimization for that field, right? I mean, health, management, and for management, right? Hospital management, hotel management, like public policy management, you name it, there are models out there, and they do use this for those types of problems. So thank you very much. Any questions?
Questions?
Yeah, I have a question. So what is next for you in your research?
So I am
not that you even scratch the surface of what you do, but
yeah.
You sound like you're on his committee.
I've been getting very interested in the decision-making side of this type of stuff. So in particular, it's called multi-criteria decision analysis. And so dealing with things like preference orderings, right? So if I have let's say I have my Pareto set. Well, great. How do you pick amongst all of those, right? Because even here, right, that's the best that I can do for my original set. But now I have to choose amongst what, maybe 20 points, 50 points, right? How do you pick that? And so that gets into trying to model people's preferences and coming up with right, mathematically rigorous ways of expressing those preferences. There's lots of different methods for that. But basically, it comes down to, it uses a lot. And so for those of us that are more of a pure math persuasion, which I used to be, it uses a lot of order theory, right? So when you talk about equivalence relations and partial orderings and lattices and things like that. So that's where I'm getting into. That, and in addition to group decision making, right? So if everyone's expressed, if you have a committee of people and everyone's expressed their preferences, how do you aggregate that together, right? So that's where I'm going with my research.
Other questions? Can you go to your previous slide? That one right there. The reference, can I find in that book where that business about the YP being in the boundary?
Yes.
I think that's, that kind of.
Yeah, this is the textbook that was used in my my initial course on multi-criteria optimization. And it's pretty good. It's quite comprehensive. The writer Ergot, so our own Dr. Wieczek, Margaret Wieczek, she's the one that does all the multi-objective stuff here. She told me that she did maybe what's it called, sabbatical to a German university, and Ergot was there as a graduate student. She taught some lectures on multi-criteria optimization. And what she told me was that basically this book was more or less her lecture notes. Right? So he compiled her lecture notes, expanded things, right, all of that, but then she cited left and right in the book, so. So it's a very good book.
Other questions?
This is really open in general, but what are some of the difficulties that you face with the problem that you're working on? Like, if you could describe in the most vague general terms possible.
Yeah. So right now, what I'm looking at is a lot of these decision analysis methods are really best for small problems, where you or your committee are using 3-4 criteria on, 10, 12 different options, right? Kind of like our car example, right? Where it's just much smaller and it's easier to manage. But the grant that I'm on, we're dealing with problems that we're talking 30 to 40 objectives, objective functions, 300-400 variables, right? And the Pareto set itself, if you were to solve that whole problem, is like 10 to the 16 different points. So, right, thinking about ways and trying to figure out ways of like, okay, so if I have 10 to the 16 different choices to make, how do I analyze that, right? Because you don't want to necessarily lose information, right? Because just throw out half of 10 to the 16. Well, what if one of those halves was actually the one I wanted, right? But how do you still manage just the overload of data? And how do you manage, if I, like the weighted sum method, right? If I'm trying to say which objectives are important to me, but my weights have to sum to 1, but I have 30 objectives, right? I mean, you're getting to like goofy little like 0.0012. Like, what does that mean for a weight, right? What does that mean for, that's how important that objective is for me, So that's what I'm most interested in. That's where the fight is, the research fight.
Other questions?
So I want to ask about the relative computational efficiency of these methods. So is there anything to say about the weighted sum versus the epsilon in terms of computational efficiency of solving these problems in practice?
So as far as I know, they're about equivalent. They're definitely better suited for nice problems, but computationally, right, it's about the same, right? The main issue, the bottleneck for all of these methods, for these two methods anyways, is so let's look at weighted sum. Is right, we trade off P objectives for however many problems, right? So now you're actually solving entire problems, and you're going to solve it over and over and over again to get some sort of representative sample of what your Pareto set is. So that's really the bottleneck. But the actual implementation of it, there's plenty of really good solvers that will solve it quickly enough. Right? The main issue is, right? So for something like weighted sum, it would be, well, how many weights do I need to go through, and how many times do I have to iterate through with these weights? And same thing with epsilon constraint, right? How many epsilons do I need to try and go through to find something that's representative of this? So the bottleneck is all of the problems. So they're about the same. Is the long and short of it.
So you're saying in the project, there's like 10 to the 16 like different like options in the Pareto set. Have you all found like a kind of way to represent that by some constraints or?
So no, that's not the approach that we're taking. The approach that we're taking is decomposition, right? So basically, right, if we start with this big problem, the main idea is rather than trying to scalarize, 30 objectives, let's say, the idea would be to say, okay, let's split it up into smaller multi-objective problems, right? And let's say each multi-objective problem is 2 to 3 constraints, 2 to 3 objectives, right? And so then I'm again, the trade-off is now I have a bunch of more problems to solve, but they're at least easier to deal with, right? They're at least easier to analyze. And so then the math happens when you have to take solutions to each of these subproblems and put them together for a solution of your big problem, right? Because you might have a predicate, right? If I do F1 and F2 in one subproblem and F3, F4 in another one, those are not necessarily the same Pareto sets, and they may not even be the same efficient solutions, right? But I have to put them back together so that it's at least weakly efficient for the big problem. So that's the way that we're doing is decomposition rather than scalarizing.
All right, I have just one last question.
Okay.
So when you're dealing with like these real world problems, can you look at the geometry of the feasible region and like exploit, like use that to kind of help you solve your problem? But if it gets super big, then maybe that's completely hands off. Is that ever an option?
That is definitely an option. There are some methods that will do that, right? So, for example, multi-objective linear programming, right, definitely exploits the structure in the same way that linear programming does, right? The simplest method and all of that. So you can, but oftentimes, again, right, it's so big that it's just I'm not going to take the time to figure out that structure. It's like no, and it probably doesn't. So, because right, you end up with a lot of piecewise functions, you end up with a lot of binary variables, you end up with a lot of just weird stuff. So,
Others? That's a good question. Any, or let's thank our speaker. Well, spring break is upon us. You know how we're doing. Usual rules apply. Pizza's got to be done. So, thanks a lot.